Hello, I'm Thomas McGrain, residing in Pennsylvania. I have experience as a technical writer with an anesthesia company back in the early 1980s to mid-1980s. I also completed successfully a respiratory therapy course at the trade school on Long Island back about that time. And back in the early 1980s, I built my first prototype for a gas-powered, autonomous patient ventilator for either long-duration use or bottle mounting for rescue resuscitation. And this is my second prototype that I completed over the last month based on my memories of the first one decades ago. And this is at this point a proprietary design, but I'm creating this presentation in an effort to save lives as we're now enduring the beginnings, or certainly the ramp up to the COVID-19 pandemic, now escalating very quickly in the United States where I reside. And I am going to describe this working prototype, and it can be either patient room gas outlet mounted. It will be packaged in a very small package owing to the low component count, while still maintaining functionality in many respects, an almost infinitely adjustable functioning ventilator circuit. And of course, this being a prototype, there are certain unrefined aspects to it, and I'll describe that. And beginning, this is a feedback controlled timing circuit comprised of a cylinder actuating and deactuating a detented valve to supply not only the timing circuit, but the patient flow control to a direct flow pilot valve. And I will describe, as you can see, the valve is being actuated by pressurizing cylinder, a single acting spring-loaded cylinder with oxygen-compatible seals and lubricant, as will all the components be in regular production. And beginning with the cycles, here we go. Inhalation, exhalation. Inhalation, exhalation. And that valve on inhalation is feeding a timing circuit. The first stage being the inhalation timing control, comprised of a variable valve and a restrictor, and of course the pressure gauge is for prototype testing, and that in turn goes to a check valve that imparts a small back pressure to aid in a smooth operation of the cylinder and the timing circuit. So that feeds the cylinder actuating the valve, and on the exhalation cycle now, the cylinder evacuates through another restrictor over to a flow control valve to control the timing of the exhalation cycle, and between the inhalation and exhalation cycle controls, one can attain various ratios of inhalation and exhalation. I've currently set it for a ratio of 1 to 1.5, which might be considered an average or typical cycle ratio. And backtracking from the source valve, there is a tap of pressure, which goes through another restrictor, thereby reducing the pressure loss in the timing circuit to maintain that integrity. But that small pressure is again controlled by another valve that controls the pilot actuator of a flow amplification pilot valve, and a balance for timing between two restrictors and a valve. Here's another restrictor on the exhaust of the pilot valve that gives me flow timing control, and when balancing controls a plateau at the peak of the inhalation cycle. Now, as you can see, the timing is very obvious. However, this is not a true indicator of the breathing cycle, which is varied not only by the cycling actuation, but by the inhalation and exhalation controls, and the flow control. And here I'm showing some indicated flow, a minor volume, extrapolated to be about 500 milliliters or 600 milliliters, tidal volume at about a 14 breaths per minute rate, and it can be increased later through minor component changes. And keep in mind, this is a prototype to demonstrate the design and the function. And here's my source pressure, a regulator to simulate a typical patient room hospital pipeline gas pressure for medical air, and naturally an on-off ball valve to control the operation of the circuit for working on it. But now, from the flow meter, the outlet of the flow meter from the patient supply gas, we go to a new design I came up with for a breathing circuit control valve. On the right top is your source for the inhalation cycle, passing through a check valve on the right into a chamber, and on the other side of that chamber is another check valve in the same orientation, whose operation is controlled by a tap on that inhalation pressure to control an internal bladder to open and close the check valve, allowing the exhalation through that center tube I'm showing you here. And just for demonstration purposes, I have the tube in a minor glass of water, about a ½ inch of water, to minimize back pressure, just to demonstrate the exhalation cycle through the valve. And here's a simply prototyping converted standard off-the-shelf pressure gauge with a homemade graduation for centimeters of water. on the breathing circuit, and naturally the breathing circuit would be disposable. And here is a very crudely built temporary pop-off valve, a safety pop-off or safety relief valve for the patient breathing circuit. I designed it for 30 centimeters of water, utilizing a water bottle turned into a valve seat with a calculated spring rate and a Teflon tape spool as a valve within the seat, tapped into the breathing circuit. And here, as crude as it is my simulated lungs, a 1 gallon or 3.8 liter volume with added tensioning to simulate the resistance or compliance of lungs. Now the breathing circuit control valve would be much smaller in production, and it would also incorporate the pop-off valve and a PEEP control valve. The breathing circuit, of course, as I said, would be disposable for infection control, patient safety, and the valve, I believe, could be produced as disposable. And in the use of medical grade compressed gas to ventilate a patient or to resuscitate, an additional oxygen tap in the breathing circuit would be included to vary the percentage of inspired oxygen. So, summarizing the functionality, the timing circuit, the flow control, a number of variables are available. First of all, inhalation, timing, exhalation timing, and as a result, ratio timing, breaths per minute, by virtue of the two controls, plus the flow control, the pilot pressure for the pilot valve, resulting in a higher flow, kind of like a transistor for pneumatics. And so we would have inhalation, exhalation, ratio, flow, tidal volume rather, duration of gas delivery, perhaps I can incorporate some capacitance in the breathing circuit to allow the PEEP. That was one design consideration I had. And this is kind of interesting. I'm on a limited budget and I could not afford to buy a bellows assembly, so it made me think, could I utilize a good quality flow meter? And I thought, well, I could if I provided a panel mounted, color coded, quickly understood graphical chart of liters per minute flow versus time and inhalation duration, perhaps like 1-2 seconds, etc. And from the panel mounted graph and the indication on the flow meter and a simple timing of the cycle, one could fairly accurately determine tidal volume in milliliters. It's not etched in stone yet, but I'll explore that possibility down the road. Right now, I'm interested in saving lives. I invented this back in the first years of the 1980s, and now I built the second prototype. Today is, March 29th, 2020, and this is my second prototype after three and a half weeks of component changes and additions and tuning, basically testing and refining the design. So ideally, with the severe shortage of ventilators under these circumstances, and a future application being for rescue and first responder use in resuscitating people, I can envision not only rescue, but police officers having a portable unit with a tank and the attached ventilator and a mask in their car for quick response. As you know, what is it, 7-8 minutes a person has? So an important feature of this is the low flow of the timing circuit. Almost all the available gas from a bottle or from the pipeline goes to the patient for direct use. Minimal gas is lost as a result of the cycling and exhaust through the restrictors. And of course, they could be routed to gas scavengers or directly vented, depending on the circumstances and use. As you can see, it's a low component count with many functions. And one can easily see that these components could be compactly enclosed in a small, durable container for direct attachment to the DISS outlets in a patient room, or to a high pressure gas bottle with the use of a regulator. And of course, this is still a work in progress, but I'm sharing the design philanthropically, I believe. We'll see how that works if anybody's interested, in an effort to save lives. Which, if you think about it, could be my own, as I'm an older gentleman. Not my primary motive, but a little levity there. So, this is my ventilator invention. I'm Thomas Patrick McGrain, residing in Pennsylvania, and it's all about saving lives. Until which time that a situation is agreeable. The design is proprietary, but I'm motivated by saving lives, not personal gain. Thank you very much. I hope you like my ventilator. Works very nicely.